Hello, this is Jennifer Dassinger with A Plus College Ready, and welcome and back to part 2 of Vesper and molecular structure. So we just finished discussing hybridization with rules and regulations. So let's look at our Vesper structures and our molecular geometry shapes. So if you look at a linear shape, it exhibits a hybridization of an S and P, and that is where that spherical shape and the pi shape or P shape will overlap, and therefore a linear will have an S and P shape. The next one is if you look at a trigonal planar, boron trifluoride will exhibit an sp2 overlapping shape. Now, you can also look at it like this as a quick shortcut. 1s and 2p is 3. So, if you have a trigonal planar, tri is 3. Kind of look at it like that, I guess. If you look at ammonia, remember, ammonia is going to have that trigonal pyramidal shape. And if you count the number of bonded atoms and unbonded atoms, so you have an S, P1, so start from right to left. Start with the first hydrogen on the right. That would be an S. The second, a P1. The next hydrogen, P2. And then the unbonded pair is the P3. So remember your orbital notation. You have a maximum of 3 orbits for a P, 1 orbit for an S, possibly being able to fill. So the maximum amount is an sp3 for a trigonal pyramidal. Here's a little breakdown for you. So linear has an S and a P. So 2 bonded atoms to the central atom. Kind of makes sense. A trigonal planar, 3 bonded atoms to the central atom. 1 S and 2 Ps. Number of orbitals, hybrid orbitals, that's 3. sp3, number of hybrid orbitals would be 4. That would be a tetrahedral, like in our methane. Notice trigonal bipyramidal has 5 number of hybrid orbitals, so therefore it's an sp3d. Get the pattern? I think you see it now. However, here's an exclusion warning. Warning. On the AP exam, there is current evidence to suggest that hybridization involving d orbitals does not exist. And there's some controversy about this. However, in the past 4 years, I have seen the d orbital expanded valence hybridization on the test. So I'm going to talk about it and I'm going to show it to you, but I'm not going to spend a whole lot of time. So involving those d orbitals is basically any element in the third row on the periodic table will experience hybridization of the d orbital. So notice we put the d first. Now sometimes you're going to see in text where it would be written as sp3d, and that is also acceptable. Little controversy about that as well. However, most people prefer to put the d first to signify that this substance is found on the third row or past the third energy level. There you go. With that being said, just count them up. So DSP3, count it, is going to be 5 because you have 1D, 1S, and a P3. And that shape is going to be a trigonal bipyramidal. Then if you notice down at the bottom, you have D2, SP3, count them up. That's going to be an octahedral. And that's all you really need to worry about. Here's another little breakdown if you want to summarize everything that we've discussed so far. We've talked about the form, remembering that A is the central atom, or X or B is the bonded atoms, and E is the non-bonding electron pairs or unshared pairs. Then we have the molecular geometry shapes and the hybridization that is associated with it to the central atom. Sigma and pi bonds is also a crucial concept that is discussed on the AP exam, off and on. Sigma, again, is that spherical shape that in the region directly between the two bonded atoms. A pi bond exists in the region above and below a line drawn between those two bonded atoms. Essentially, here's the summary. If you have a single bond, you're going to have one sigma. If you're going to have a double bond, like in our carbon dioxide, you're going to have one sigma in the double bond, and then the other line will represent one pi bond. If you have a triple bond, such as nitrogen, where you have nitrogen bonded to nitrogen, in a triple bond, you'll have one sigma representing one line. The second line would be a pi bond, and the third line would represent a third pi bond. That's really all you need to worry about. But here's some examples. So if you see ethane, notice the single bond between the carbon to carbon, it's a 1 sigma. Notice ethene, little organic for you. Notice the suffix changed to a ene ending when I have a double bond. The eth stays the same, and eth represents the two carbon atoms. So within that double bond, in that one bonding site, I have one line that represents 1 sigma, and the second line represents 1 pi. Now notice ethyne, remember eth meaning two carbons, the yne meaning suffix meaning triple bond. So in a triple bond, one line represents a sigma, one line represents 1 pi, and another line represents another pi bond. That's the visuals for you. Don't forget our friend benzene that we've talked about before. Benzene is the localized model of that resonance structure. It creates that hexagonal structure of the alternating single and double bonds. And when you see that, it helps to explain how those pi bonds are moving around. So the electron density from those pi bonds can be distributed symmetrically, creating that ring. That's really the justification for a resonance. If you have any other questions or continue to practice is really all I can give you helpful hints on. Your teacher will provide many more examples for you. Practice, drawing Lewis structures, writing the molecular structure names, the shapes, doing the VSEPR, hybridization, and the angles. And outside of that, review your concepts of bonding. This is a crucial part of the AP exam. It is big idea number 2, and keep studying and good luck to you. Have a great year and good luck on the AP exam.